So finishing up 2.3, let's show that this transformation, a matrix times the vector, is a linear transformation. So let A be an M by N matrix, and let the T be the transformation Rn to M, defined by the product, basically what we've been doing, right? A times X for each column vector and in Rn. So basically, the definitions of matrix multiplication with vectors allows us to do the transformation. So let's just see how that works. So let's we'll just pick U and V. So pick U and V be, and these are appropriate size vectors. These will be column vectors in Rn. You don't really have to worry if they're column or vector. It's just notation basically. Okay, so let those be in Rn. So now you can show one that T of U plus V is equal to A times. So the transformation is A times that vector U plus V. And by matrix multiplication, we know that is AU plus AV. We can write it like that. But this is the linear transformation. So that's equal to T of U plus T of V. So it satisfies 1. Let's write 1 down. And then 2, let's just make this in like sentence form over here. And then 2 is scalar multiple. So we need to place R in the right set, make it arbitrary. And so then T of R times U. Now remember, you can't factor it out. That's what you're trying to show. But that is defined to be R. No, I'm sorry. A times that vector inside, which is R times U. And just by scalar multiples, we can take out that R. So that's equal to, equal to R A times U. I don't need those parentheses there, do I? And AU is the definition of the transformation. So that's RT of U. And so therefore, T, as defined above, is a linear transformation. So now, last thing I'm going to do in this is, and we'll do a couple things on terminology, but is we're going to go through example 7, but I'm going to do it a little different way than they did it in the book. So this is example 7. I'll just say done a different, let's say method, a little bit. So this is what it says. This will take the rest of the time pretty much. So let's let U be the vector -1, 2, which we can always make column vectors, right? And V, actually, you know what? I'm going to bring this back over here so it looks a little better. Okay, and then V, I was going to change what I had written, but this is fine. Be 3, -5, and just note those are vectors in R2. Okay, and let T be the transformation, a transformation, R2 to R3. So it would be a linear transformation. Excuse me. Be a linear transformation such that t of u is equal to the vector 2, 1, 0, and t of v is equal to the vector 5, negative 7, 1. Okay, so this is, haven't talked about this yet, but we're going to find what's called a standard matrix representation A of that transformation. So we're going to find a matrix that gives us that transformation. So find a standard matrix representation A of T. And then once you do that, compute, it's like once you have it, then do something with it. Then compute T of negative 4, 3. Okay, so we have that T of the vector negative 1, 2, which is my u, is equal to negative 2, 1, 0, and t of 3, negative 5 is equal to 5, negative 7, 1. Okay, that's everything there is given. I just wanted to put in what u and v actually are, so you see what we're trying to do. Now, A is a matrix. You're basically saying a matrix times this vector is equal to this one. So we're going to just place it into a vector and put variables in. So it's done a little differently than they may have shown you there. So A, let me say this now. So A needs to be what size matrix? So you're going from so when you have a matrix multiplication, you can erase this. So if you have matrix multiplication, the insides need to match. So let's just see if this works. And then this needs to be, this other matrix was it's a column vector. So those are the vectors. So this is the column vector. This is a 2 by 1. So this will be 2 by 1. So we're going to end up with a 3 by 1. Okay, so the matrix A needs to be a 3 by 2. Okay, so we're going to do this. I'll leave that there for a second. So when we look at this, we are basically, what you're doing is you're determining. So A is a 3 by 2, and you'll see this notation. A is, you want to find out what the transformation is of the standard normal vectors like this, and those as column vectors, where E1 is 1, 0, and E2 is 0, 1. So what you'll do is we'll just construct a matrix that's a 3 by 2. We don't know what they are. We'll call it x1, x2, y1, y2, and z1, z2, and then that's going to be times the vector negative 1, 2, equal to, and then what does that need to be equal to? that product we want is it's given. The given product is up here. That needs to be negative 2, 1, 0. So that's negative 2, 1, 0. Let's go ahead and erase that. So we have that, and we need to have that this same matrix right here, I'm highlighting it, that same matrix times the other vector, which was, where is it, 3, negative 5, has to equal the other vector. And what you end up doing basically is just solving a system. But I wanted to write it out like this so that you can see what's really going on. The book kind of just says, here, it's all the same, row reduce, it's all fine and dandy. So now, do this product, right, for each one, like that, and you'll see you end up with a system. So what you get then, and I'll just write it up here, you get, so look at that and then do that product. You get, I guess you can see it here. So you get, there's going to be 3 of them. Negative x1 plus 2x2, and that's going to be negative 2. Then you'll get negative x1 plus 2y2, and that's going to be 1. And then you'll get negative z1 plus 2z2. That's equal to 0. That's for the first, that's for the first matrix here. Then we're going to do the other matrix. And you get, with that product, 3x1 minus 5x2 equal to 5. And you can see what I'm doing, right? 3y1 minus 5y2 equal to negative 7. And then again, 3z1 minus 5z2 is equal to 1. And so you end up having then this system of x here, and then you have this system for your y's. And then you'll have this system for your z's. And so what you get then is negative x1 plus 2x2 equal to negative 2. 3x1 minus 5x2 is equal to 5. And you are literally just solving that system. And you do that for each case. Negative x1 plus 2y2 equal to 1. 3y1 minus 5y2 equal to negative 7. Negative z1 plus 2z2 equal to 0. 3z1 minus 5z2 equal to 1. And then you solve that system. Okay, so solve each one. And I'm going to speed things up a little bit. It's a lot of work. There is a fast way of doing it, but it's not really about speed. It's just I want you to understand what they're trying to show you. So when you solve this, this is what you get for each system. So you get x1, x2, so you get the whole matrix. So you get A. So now you can say A, and that's easy. They're easy to solve. I mean, it's just a 2 by 2. However you want to solve the 2 by 2. So your matrix A is that, just put in the variables, and you have it. So it's 0, negative 1, and then you can check it just by using your calculators and stuff. Negative 1, 4, and 2, 1. And so that was part A, is finding the matrix. Part B was use it to calculate that transformation, which was -4, 3. And so it's that matrix times -4, 3. And that's your transformation. So what was I doing? Was I verifying? Yeah. Oh, this was verify. So first, I guess I was going to verify and then use it to do the, yeah. So this is just verifying it works. So 0, -1, -9, -4, 2, 1. And then times -4, 3. And we know what that should be. You don't have to check each one. I mean, you don't really have to check it. It's just nice to do it when you're studying this stuff. So you get negative, right, where was I at? Oh no, that was what we wanted to do. Okay, so that is what's being, so compute that, and then the other one I did check it. I checked that one, okay. So this is what was being asked. All right, so this then, and when you do that, just do your calculator and do your product. You get -3, or do it by hand, either way. Okay, so that works, or that's what you get. Okay, then you can verify that it is working by doing the transformation of what's already given. So what was already given is 3, -5, and then it's A times that. So put in A, whatever that is, and then check to see what should you get. You should get 5, -7, 1. So it should be 5, -7, 1. And indeed, it works. So you may want to do, you probably would want to do this first to double check that you have the correct matrix. Now, there is a faster way of doing this that the book went through, but I don't know if it made sense of why you're doing it. But that's how what you're doing. You're trying to find a matrix product that gives you this. Okay, and so in this case, you really are just solving that system. Each system, basically. Okay, let's finish this up just with some terminology. I'll just say literally some terminology. Of linear transformations. And we will do more of this in, like I mentioned earlier, or the other video, in chapter 3 on the more general case of vector spaces. But let's introduce some of this. Let's let T be a transformation from Rn to Rm, be a linear transformation. And then you call it with a standard matrix representation. Just like above, right? So you have T of x is equal to AX. Then 1, the range. So the range of T of Rn is the column space of A. So that ends up being the column space of A in Rn. 2, we don't do row space, by the way. It's not defined here. Okay, so, or used much. Okay, so what's called the kernel, first time you introduce that, the kernel of T is the null space of A. And it's abbreviated ker-T. And then we will look at that more generally speaking. It's basically what maps to 0. So you're going to have all these, you have this big set like this and all these vectors here. And so the kernel is what's being mapped to the 0 vector. So if that's the case, this set over here is called the kernel. Okay, we'll get to more of the details later. Three, if W is a subspace, so if W is a subspace of Rn, then T of W is also a subspace of Rm. So is a subspace in Rm. So in other words, the linear transformation T preserves subspaces. Okay. So we will, there's a number of things left in 2.3 that they go on and on about, and we redo it in chapter 3. So we'll wait till then. So just be familiar with this, apply some of the ones I've already been doing with matrices above, and study the basic concept of a transformation. Okay, and that'll do it for all of chapter 2.